All right, hi everybody. Reminder that your chapter 9 slides, not the extra ones, but the ones we didn't cover in class are covered in a recording. So I mentioned that on Monday. Your last achieve homework is due at the end of the day next Monday, 11:59 p.m. This is the same time that the remaining learning curves are due. So there's one for 7, 8, 9, 10, and 11 that you can complete by Monday. Yeah, so each one will count towards 1 point on either your unit exam 2 or your final exam. I'll distribute them to increase those scores after your final exams are graded. Some of those learning curves, I can't remove individual questions, so they might have questions that are not what we've covered in class. So keep that in mind. If you ever have a question about one of them where you're unsure if we covered that in class or not, just take a screenshot and send me an email and I'll let you know. I have office hours today at 2, tomorrow at 1:30, and then Monday we don't have class, but I'll be on Blackboard Collaborate during class time at this time and for my 9 a.m. class. So that will be like an office hour. So I'll just be there for the hour. If questions came up as you were studying or working through problems, feel free to just hop on Blackboard Collaborate where we have recitation, and I'll be there. So that will be next Monday.
Next Friday, we're not going to be here.
No. So our exam is Wednesday at 11. We have an hour and 50 minutes, and that's the last time we'll meet. Yeah. Okay. I just want to make sure I turned the mic on for the recording. Yeah, I did. Okay. All right, so we talked about drawing Lewis structures. And remember, elements will form covalent bonds to close their valence shell. So we already talked about carbon and oxygen. Carbon has 4 electrons in its valence shell. It needs 4 more to have a full shell, 8 electrons. So carbon typically makes 4 bonds. It's most stable when it has 4 bonds. For the same reasons, nitrogen is most stable with 3 bonds and oxygen is most stable with 2 bonds. So you can use this pattern as you work through Lewis structures, drawing Lewis structures for molecules, to draw the most stable Lewis structure. So let's go ahead and work on this one here. We have formaldehyde, so H2CO, aqueous solutions of formaldehyde. You may have heard that word before. They're used to preserve biological specimens. So we're going to draw the Lewis structure of formaldehyde. So remember, first step that in the steps that we've outlined is to determine the number of valence electrons. So we have 2 hydrogens. Each hydrogen contributes 1 valence electron. We have 1 carbon. Carbon contributes 4, and we have 1 oxygen. Oxygen contributes 6. So we have a total of 12 valence electrons. Next step is to arrange atoms so that the atom that typically creates the most bonds is in the center. You look at our last slide, we have hydrogen, which only makes 1 bond, carbon, which makes 4, oxygen makes 2. So carbon will be your central atom. So try working through the structure for a minute and then we'll review it. I want to see how you all are doing.
Oh, that's an 8.
Once you've arranged the 4 atoms, 2 hydrogens, carbon, and oxygen, count how many electrons are in the bonds. It's going to be less than 12. So you need to add lone pairs to outer atoms that can hold lone pairs. Then double check that your atoms have closed shells. When you finish, you might start on the next slide. All right, carbon creates the greatest number of bonds, so we'll arrange carbon in the center and then put a single bond between carbon and each of the remaining atoms. Doesn't really matter at this point where you arrange the atoms, as long as you have, at this point, 1 bond to oxygen, 1 bond to hydrogen, 1 bond to the other hydrogen. Remember, hydrogen can only make 1 bond, so it'll only ever be connected to 1 other atom. Carbon can make 4, oxygen can have more than 1. Yeah.
So if you're, I know this is kind of down the road, but if you're doing a double bond for the dots, don't you take the bottommost one? You know what I mean?
For the dots?
Yeah.
It doesn't matter.
Oh, okay. All right.
Okay, so at this point in bonds, we have 6 electrons. That means we have 6 electrons remaining. So if we follow the steps for creating Lewis structures, we would add the remaining 6 electrons to our outer atoms, but not to hydrogen. Hydrogen can only hold 2 electrons in its valence shell, so that's the 1 bond. So if we put all 6 around oxygen, we've used all 12 valence electrons. But looking back here, carbon only has 3 bonds. It only has 6 electrons in its valence shell. So it will be most stable if it can have a 4th bond. And so we'll do what we looked at last time, which is moving one of the lone pairs from the oxygen to then create a double bond. Now, if you know, without going through that whole step, that carbon, you notice carbon only has 3 bonds and it needs 1 more. Well, you can look at the other atoms bonded to it, see which one can have a double or triple bond, and oxygen is the only one that cannot have double bonds to hydrogen. So there's our final structure. We have all 12 valence electrons, we have 8 electrons in bonds, and 4 electrons in lone pairs. Another thing we discussed at the end of class were these structural formulas. So if we call them carbon chains, so longer carbon chains, where we don't have one central atom in these structures. In the previous example, carbon was our central atom and that was bonded to everything else. But something like propane, we have a carbon bonded to 3 hydrogens and another carbon, bonded to 2 hydrogens and another carbon, bonded to 3 hydrogens. And so this can be written with those groups, so CH3, CH2, CH3, and that gives us some information about the bonding pattern in that structure. So if we go to our next learning check, we have a acrylonitrile used to manufacture polymers for synthetic fibers. We're drawing the Lewis structure of acrylonitrile. So we could count valence electrons, and we should do that to double check. But if we just look at the structural formula, we have H2C first. So that tells us we have a carbon bonded to 2 hydrogens. Then we have a CH. So this carbon that we've already drawn is bonded to another carbon that's bonded to a CH. And then we have CN. So second carbon's bonded to a third carbon, which is bonded to a nitrogen. So just based on the structural formula, we can deduce this connectivity of atoms. Now we see that atoms are not closed shell. We have to fill in more bonds, fill in more electrons. We can use not total number of valence electrons to do that. But this is a good place to start if you're given the structural formula, is to draw out the connectivity. Okay, so total number of valence electrons. We have 3 hydrogens, so 1 from each hydrogen. We have 3 carbons. And we have 1 nitrogen, which has 5 electrons. Yeah. Just 1. So when we're counting total valence electrons, we're thinking about an individual atom with a neutral charge. So hydrogen, if you draw the electron configuration of hydrogen, it's 1s1. So it just has 1 electron. But hydrogen will bond to obtain another, to have a full shell. Okay, so we have 20 total valence electrons. We currently have 6 bonds. So we currently have 12 electrons in bonds, which means we have 8 electrons remaining that will either need to be in double or triple bonds or as lone pairs. Next step is when we're working with this larger structure, next step, I think, is to check to see which atoms are closed shell. So all of our hydrogens are all set. They've got 1 bond. Nothing else is going to happen with the hydrogens. This first carbon only has 3 bonds. It only has 6 electrons in its valence shell. It needs 1 more bond. Where can we place that double bond? Yes, I heard it from a few students. In between the first 2 carbons. We can't put it to a hydrogen. Hydrogen can only have a single bond. So we'll put a double bond here. That takes care of the valence shell of the first carbon, now has 4 bonds. The second carbon now has 4 bonds. So both of these carbons are taken care of. Next carbon only has 2 bonds. Where can we add another bond? Between the carbon and the nitrogen. Why can't we put it here?
Because that carbon in the middle is already full.
This carbon in the middle already has four bonds. It cannot hold more than 8 electrons in its valence shell. So this carbon, we can make a double bond to the nitrogen. Oops. But that's still only 3 bonds for carbon. Needs 1 more. Well, we can add a triple bond there. So with those additional bonds, we have 18 electrons in bonds. So we have 2 more electrons that need to go somewhere. Where do they go? On the nitrogen. So nitrogen is the only open shell atom. It only has currently, well, before I added the lone pair, it had 6 electrons in its valence shell. It needs 2 more electrons, so that's a lone pair. Yes.
Does it matter where we put the electron?
At this point, no. You could just not where the bond is. So you could put it up here or on the bottom. Yeah.
Could you split them up or?
No, they have to be paired. Yeah. If they're unpaired, these are called radicals. These are very reactive. It represents something else. So pair them. Yeah, good question. Okay, so next slide here is really just to show a few different ways that we can represent molecules. So water, H2O, 2 hydrogens and an oxygen. Up there we have the chemical formula. All that tells you is the number of each type of element that's present in the molecule. The structural formula tells you how atoms are bonded and what atoms are bonded to each other. So we see that the oxygen is bonded to 2 hydrogens. The Gault and Stick model shows us geometry. So we'll talk about geometry later on Friday. And this shows that these hydrogen atoms are not 180 degrees apart. There is a acute bond angle between them. And the bond is represented by the stick. The spheres represent each atom. In the space filling model, we can't see the bonds, but this is most similar to what exists in the world. In the real world is because the bond, what a bond is an overlapping of orbitals. And orbitals are spaces around the nucleus. So this shows that the hydrogen orbital is overlapping with the oxygen orbital on both sides. Gault and Stick model emphasizes the bonds. Structural formula tells us what atoms are bonded, but doesn't tell us the shape. So, a bunch of different ways to represent molecules. Okay, so let's move on to resonance and formal charge. And before we talk about what this is, let's draw the Lewis structure for NO3 minus. So I've calculated total number of valence electrons at the top. 5 from nitrogen, 18 from 3 oxygens, and then we add 1 more because we have a minus overall net charge on the molecule. So that's a total of 24 valence electrons. Now what do we do? After we calculate valence electrons, what's next? Yes, we have to decide which element we're going to put in the middle. Which element do you put in the middle? I hear nitrogen. Why nitrogen? Because that's a good clue. There are 3 oxygens. Yeah, so nitrogen typically makes 3 bonds. Oxygen typically makes 2. So nitrogen is most stable with more bonds than oxygen. So we put the element that creates more bonds in the center. That way nitrogen can bond to all 3 of the oxygens. So nitrogen's in the center. So we have 6 electrons in bonds, which means we have 20, not 8. We have 18 remaining. So we can distribute, next we distribute to outer atoms to close their shell. So each oxygen to have a closed shell needs 6 more valence electrons, and that takes care of all 18. But we have a problem here. What's our problem? The nitrogen, the nitrogen doesn't have a full valence shell. It only has 3 bonds. So what can we do? Okay, so we'll take a pair from an oxygen and share that in a double bond with the nitrogen. Which oxygen will do that? Any of them, yeah, it doesn't matter. So it doesn't matter, we could pick any of these three oxygens to make a double bond. So let's say we pick the oxygen on the bottom, and I'm going to show that curved arrow, which demonstrates that this pair of electrons that starts as a lone pair will now be shared in a bond. And that will give us what we call a resonance structure, where we have everything is the same except for that oxygen is now a double bond. My pen is like dragging a little bit. Sorry about that. We could also, so that's the oxygen on the bottom. We could take the oxygen to the right and share a pair of electrons with nitrogen, but we can't have two double bonds to nitrogen at the same time because that would put too many electrons. And it's valence shell, so we have to also, if we're going to create a pi bond here, a double bond here, then we have to make this a single bond and put those electrons back on oxygen. And then lastly, we could use the oxygen on the top right, put those electrons, make them a double bond, and that will give us our last resonance structure. And all of these have a net minus charge, so I'll just add a charge on each of these, minus charge. Okay, yeah.
I thought nitrogen was most stable.
It is most stable with 3 bonds. We'll get to that. Great question. We'll come back to that in a couple of slides. Okay, questions on how I did this? I kind of did a lot on one slide. Yeah. Thank you. Yeah. Okay, so we're just changing the placement of the double bond, which is, all of these are valid resonance, they're all valid Lewis structures. This is a valid structure, but it's really unstable. This version of NO3 minus is unstable because we have an open shell nitrogen. But all 3 of these are equally valid, equally stable, equal energy Lewis structures of NO3 minus. These are called resonance structures. So resonance structures are connected by a double-headed arrow. I drew that on the last slide. I didn't call it out, but this is an arrow that we use to show that the structure on the left, the structure on the right are resonance contributors of the same molecule or the same ion. The true NO3 minus ion is a hybrid of all 3 resonance structures. So in reality, NO3 minus does not ever exist as only this structure, or only this structure, or only the 3rd structure. It exists as a hybrid of all 3, where we have partial double bonds between nitrogen and all of the oxygens. So let's see. The true character of the anion is a blend, or I like to use the word hybrid, mean the same thing, of all 3 resonance structures. Now, we haven't talked about this in detail, but single bonds are longer than double bonds. But experimentally, if you measure the bonds between nitrogen and oxygen in NO3 minus, their length is shorter than a single bond, but longer than a double bond. So it is somewhere in between. It is a hybrid of a single and double bond. Now, usually when we're drawing structures, we will represent an individual resonance structure or all of the resonance structures. We don't often draw the hybrid. The resonance individual structures help us understand properties of this molecule or this ion. So we often draw those individual structures. Now I mentioned that this first structure here is a valid Lewis structure. It follows our rules. We just have an open shell nitrogen. We can use that rule and the rule about formal charges to pick the best resonance structure. So formal charges, which we'll learn how to calculate those, help us determine the most stable Lewis structure. So to calculate formal charge, now important, this is formal charge of an atom. Net charge, like NO3 minus, that's the net charge of the molecule. That's the sum of all formal charges. Formal charge we calculate for an individual atom. So to calculate formal charge of an atom, we take the valence electrons of the free atom, which are the values that we've used to calculate total valence electrons. So 1 for hydrogen, 4 for carbon, 5 for nitrogen. Then we subtract valence electrons that are assigned to that atom in the Lewis structure. So you have to draw the Lewis structure to calculate formal charge. And what we mean by valence electrons assigned to the atom is the number of bonds and the number of unpaired electrons. We'll calculate formal charge for atoms and NO3 minus on the next slide, and we'll use that formula. So the sum, remember we calculate formal charge for an atom. If you add together all formal charges for all atoms in a molecule, that will equal the net charge of that molecule. So if you have a neutral molecule, then the sum of all formal charges is 0. If you have, for example, NO3 minus, the sum of all formal charges will be -1. So the best Lewis structure, if you can draw multiple for a molecule, the best Lewis structure, meaning this is the most stable Lewis structure, it's the one that contributes most to the hybrid, is the one that results in minimum formal charges. So by minimum, we mean we have the fewest atoms with a charge, and any charges are lowest values, so smallest. So a molecule with a +1 formal charge on an atom is more stable than a resonance structure that has a +2 formal charge, or a +3. Or -1's more stable than -2, -3. If we have formal charges that are not 0, then the structure is more stable. We haven't learned this in our class yet, but we will probably today. Is most stable if the most electronegative, so just write this down here first. And then we'll talk about what that means later in the chapter. So it's most stable if the most electronegative atom is assigned the negative formal charge. So we'll talk about that in a couple of slides here. But let's do the NO3 minus. We'll draw one of the more stable resonance structures. So we will have nitrogen. I'll pick the top right oxygen to be double bonded. And this has an overall net charge of -1. So I put that outside the brackets. So formal charges we calculate for individual atoms. So we'll calculate formal charge for each element, each atom in the structure. So let's do nitrogen first. Remember, formal charge, I'll write the formula up here. Okay, so we have number of valence electrons of the free atom, so a nitrogen, neutral nitrogen atom, number of valence electrons, also equal to the column number, so 5 for nitrogen, minus the number of bonds in this structure. Nitrogen has 4 bonds, so -4, and then minus non-bonding electrons. Nitrogen has 0 non-bonding electrons in the structure, so -0. So that gives nitrogen a formal charge of +1. So when we draw formal charge in a structure, we'll put that positive symbol right by the nitrogen. So nitrogen has a +1 charge. Now let's do formal charge of, we'll do the double bonded oxygen here. Oxygen is in column number 6, has 6 valence electrons. In this structure, the double bonded oxygen has a total of 2 bonds. So we subtract number of bonds, so 2. And then it also has 4 non-bonding electrons. So 4 dots, subtract 4. Double bonded oxygen has a formal charge of 0. All right, let's do formal charge of single bonded oxygen. Still column 6. Now this oxygen has 1 bond, so we subtract 1, and it has 6 non-bonding electrons, so the formal charge of single bonded oxygen is -1. Now, anytime nitrogen has 4 bonds, you have 5 -4 -0 +1 charge. Anytime oxygen has a single bond and 6 non-bonding electrons, we have column 6 -1 -6, which gives us a -1 charge. So both oxygens in this structure that are bonded with a single bond have the same formal charge. So we don't need to write that equation twice. It applies to both. So -1 for both oxygens, +1 for the nitrogen, and 0 for the double bonded oxygen. So our net charge is +1 for nitrogen plus -1 plus -1 equals -1 overall for the net charge for this molecule. So that's why it's NO3 minus, the net charge is -1. Yeah.
I'm sorry, I'm just confused about that third row. Where they subtracted everything.
So this is the formal charge of the oxygens that are single bonded. So oxygen's in the sixth column, so it has 6 valence. Net neutral oxygen has 6 valence electrons. In that structure with a single bond, it has 1 bond, so we have the 1 here. And then it has 6 non-bonding electrons, so that's this value. So we get -1. Okay, going back to an earlier question, I thought nitrogen is most stable with 3 bonds, and here we have 4. Nitrogen is most stable with 3 bonds, but it can have 4. It has 8 electrons in its valence shell. Anytime an atom is outside of its typical bonding pattern, so 3 bonds for nitrogen, it has a formal charge. So in this case, nitrogen has 4 bonds. Its formal charge is not 0. Oxygen typically makes 2 bonds. If oxygen has a single bond, its formal charge is -1. But here, oxygen has 2 bonds, its formal charge is 0. So it's possible for oxygen to have more or less than 2 bonds, possible for nitrogen to have 4 bonds, 3 bonds, 2 bonds, etc. But formal charges will change in that case. All right, let's do the next question here. So we'll determine the Lewis structure for carbonate, CO3 2-. I'll do valence electrons, and then I'll give you all some time to try drawing the structure. So we have 4 from carbon, 18 from 3 oxygens, and then +2 because we have a -2 charge, so 24 electrons. So this and all 3 of these are very equal energy. So we can just one over the other. Yeah. But if you have a structure where you have 3 single bonds, and not the double bond, that would be the worst.
And then I just get.
It's kind of because like sometimes it won't be as obvious in practice. You'll see patterns that always Okay, let's go through this. We'll draw one structure here. We have carbon, which creates 4 bonds. We draw 3 bonds, 1 bond to each oxygen. That takes care of 6 valence electrons, but we have 24, so we have 18 remaining. We can distribute them to the outer atoms, and that takes care of all 24 electrons. So this is a valid Lewis structure. But there's a better structure. What's our better structure? A double bond. Yeah, we can draw a resonance structure where we have a double bond between carbon and one of the oxygens. And we could draw another resonance structure where the double bond is between this oxygen, or another one where it's between that oxygen. Yeah.
How would the first one be valid?
Yes, good question. So it's valid because we're not breaking the octet rule in the sense that no atom has more than 8 electrons. The problem is that carbon is open shell. Now carbon can exist with an open shell, but it's high energy. Here all atoms are closed shell, so this is a better Lewis structure. Let's calculate formal charge for these. So that will also show us why the second one's a better Lewis structure, lower energy Lewis structure than the first one. We calculated on the previous slide that if we have oxygen with a single bond and 6 non-bonding electrons, it has a -1 formal charge. So that's the case for all 3 of these oxygens here. Formal charge for carbon in this structure, carbon is in column 4, has 4 valence electrons. In this structure, carbon has 3 bonds and 0 non-bonding electrons. So carbon has a charge of +1. Again, we have carbon outside of its typical bonding pattern, so we would expect a charge as a +1 charge. Now our net charge on this structure is -2, and that aligns with the formula CO3 2-. Other questions? Am I going too fast? Okay, I will continue. So we have all 4 atoms have a formal charge in our first structure, and we have an open shell carbon. Second structure, single bonded oxygens have a -1 charge. We showed that calculation on the previous slide. Double bonded oxygens have a 0 formal charge. We saw that on the previous slide. And if we do formal charge of carbon here, 4th column, so 4 valence electrons, it has 4 bonds, has 0 lone pairs, so we have a formal charge of 0. So overall, this structure has a -2 charge. So this resonance structure is more stable. Yeah.
Does the +1 mean it has 1 less electron or 1 more electron?
So it has, okay. It's complicated with formal charge because when we're talking about number of valence electrons that the atom brings versus number of electrons in their valence shell versus number of electrons owned by that atom for formal charge, those are 3 different things. So carbon as a free atom, neutral carbon brings 4 valence electrons. And we use that when we're calculating formal charge. So that's the first value. In the valence shell of carbon here, there's a total of 6 electrons because it has the 3 bonds. But when we calculate formal charge, we say in those bonds, carbon owns one of those electrons, oxygen owns the other. That's an assumption for calculating formal charge. So that means that carbon's only owning 3 electrons in this bonding pattern, 1 from each bond. And then 0 lone pairs. Does that answer your question? I forgot what your original question was.
I was wondering if the +1 is like means it's like an extra electron.
Okay, so +1 would be 1 fewer electron because electrons carry a negative charge. Yeah. So it owns 1 less electron than the amount of valence electrons it would bring. Yeah, that's what we're saying. Other questions? Okay, we'll move on to the next section. So exceptions to the octet rule. So mostly we can use the octet rule or duet rule for hydrogen to determine how many bonds the atom will make. But there are some exceptions. So boron, for example, boron's in the second row. It is stable with 3 bonds or 6 valence electrons. Beryllium, also in the second row, is stable with 2 bonds or 4 valence electrons. These are the only 2 exceptions in the second period. And for elements in the third and higher rows, they can have more than 8 electrons in their valence shell because they have access to the 3d orbitals or 4d orbitals or 5d orbitals. So remember the octet rule, electrons are most stable with 8 electrons in their valence shell. That provides a full 1s shell, or a full s shell and a full p shell. So 2 electrons in the s shell, 6 electrons in the p shell. If an element has access to a d orbital, then it can hold more than 8 electrons in its valence shell. We can start filling the d orbital. So that's why elements in third and higher rows can have more than 8 electrons in their valence shell. So let's see what this looks like for chlorine trifluoride. Now both of these are halogens. We would expect them to make 1 bond. Often they make 1 bond. Fluorine is in the second period. Chlorine is in the third. So if one of these elements is going to have more electrons in its valence shell, it's going to be chlorine. Fluorine can only have 8. It'll never have more than 8. So we'll use the same process, total valence electrons. We have 7 from chlorine and then 21 from fluorine times 3. So 28 valence electrons. Since chlorine is in the third period, we will arrange that in the center. It can have more than 8 valence electrons because it's in the third period. So we'll arrange that in the center and create a single bond to each fluorine. So that takes care of 6 electrons. We have 22 more. We start adding to our outer atoms to close their valence shell. We've added as many electrons as we can to fluorine. Fluorine can only hold 8. In our structure right now, we have 24 electrons. So we're missing, or we need to add 4 more to get to the total 28. Can't add them to fluorine, but we add them to chlorine as pairs. So here's an example of chlorine in its valence shell right now has 10 electrons. This is called a hypervalent. Because it has more than 8 electrons in its valence shell. Okay, we're going to skip the next example. I drew it here. You'll be able to see it in the recording, or if you want to draw it real quick and then practice it. We can also go over that on Monday. We're not done though. I want to cover a couple more items. I'm going to just introduce this idea of electronegativity. So I mentioned that a few slides back. Electronegativity is related to other periodic trends that we've talked about. So effective nuclear charge, atomic size, things like that. If we're looking at a hydrogen fluoride covalent bond, this bond occurs from an overlap of the hydrogen valence shell, which is the 1s orbital, and the fluorine valence shell, which is a 2p orbital. So that's what's shown here. We have a 2p orbital for fluorine and a 1s orbital for hydrogen. They overlap along the bonding axis, which we call now a sigma bond. Where we have the 1s orbital of hydrogen overlapping with the 2p orbital of fluorine. So that's how these orbitals are overlapping, how the two atoms are sharing electrons. But in reality, atoms often don't share electrons equally. So unequal sharing leads to asymmetry in bonding electron density. So the location of electrons will be nearer or around more electronegative atoms. More electronegative atoms have a greater pull on bonding electrons. So these are the atoms that have a greater effective nuclear charge. So as you go across a period, effective nuclear charge increases. So that will be to the right of the periodic table. And as you go from the bottom to the top, effective nuclear charge increases. So we say those elements have higher electronegativity, which is summarized on this slide here with actual values for electronegativity. So you can see fluorine has the highest electronegativity value. It's a highly electronegative element. And so if fluorine is in a bond, the two electrons that are shared with fluorine and the other atom are closer to the fluorine nucleus because it has a stronger pull on those electrons. Okay, we'll start on this slide on Friday.